Okay, let me just go to full screen. Okay, this is just you two, that's totally fine. Okay, so we're gonna cover a very completely different topic, which is a concept called neural networks. You may or may not have heard what they're about, especially with Google advocating its use, the Deep Dream project. I'll give a little overview of what that is. Just talking about introduction and the basic way to calculate and train them. So why do we need them? And they're basically biologically inspired models, so they're modeled after the way the human brain functions. And we'll talk about how to train them, so how to represent them in machine learning, forward and backward propagation. Those are the standard ways to manipulate and train them. Putting it all together, we're going to talk about how to train a neural network, and then we'll give a detailed example. The midterm works have been posted. You can go see your TA to get your midterm papers back. You can either get them today from 2 to 4 in ENG 426, or you can see them on Friday in the lab from 12 to 2. Okay. So, neural networks. It's yet another machine learning algorithm. Why exactly, do we need it? Do we need to know them? Yet another. Yeah, it's just you three. That's fine. It's yet another machine learning algorithm. So these have actually been around for quite some time. Like, they were quite popular back in the late 80s and early 90s, but they fell out of favor for more advanced techniques. But they recently saw a surge back in popularity, especially due to Google's use with the Deep Dream project. So they've actually come back in full force, and they're quite popular now. So they have been around for quite some time. But fell out of favor due to more, but fell out of favor due to the preference of other algorithms. It actually fell out of preference for an algorithm which is called the sport vector machine, which we'll talk about next week. So they have actually been popular for a little bit, and now they're competing algorithms, difference of other algorithms in the past. Yeah, basically, the reason why they're so popular now, it's basically due to scale. The reason why they fell out of favor is because they're really computationally intensive to train. So with all the big data craze, there's these clusters of computers, and each computer is very powerful in itself. So because of the big data craze and the hardware being pushed beyond the limits of what we're capable of, that's why neural networks have come back in full force, because we're actually able to train them efficiently because of advances in hardware and technology. Okay, so yeah, that's a very good question. Okay, so have recently seen a surge in popularity due to recent advances. I'm going to talk about a few applications in neural networks that actually are currently being used in practice, even though you may or may not know it. Okay, so applications in use. Okay, so the number one application is the Google Deep Dream project. I don't know if you've ever fooled around with it, but basically the whole point of the Google Deep Dream project is you submit an image online onto a particular processing algorithm, and what it does is that it takes a look at the image and it introduces psychedelic effects. So it's as if you were kind of like on an acid trip, or if you were like on an MJ trip. What would happen if you took an image and if you decided to take one of those substances and see what the after result would be? It's actually a pretty trippy process, and you use neural networks to actually simulate what it would be like. And I'll give you an actual example. It's actually pretty cool. So, okay, so goal is to introduce psychedelic effects to images using neural networks. And this is a great example. I actually pulled it off from Wikipedia a few days ago, which I'm actually going to show you. So let's see here. This one, it's really trippy. This I pulled off from the Wikipedia article from the Google Deep Dream project, so this is the source, is Wikipedia, Deep Dream. So this is just a normal photo of a guy and a girl, and then when you submit it to the Deep Dream project, this is the result that you get on the right. It's actually really, really trippy. So it's as if like someone made like an Escher style painting or something that's a little modernist painting. And the image, how this works is that they submitted tons and tons of example images, and they took a look at certain characteristics of the images, and what they do is they take a look at regions of the image and figure out what is similar to other images that were submitted in the past that were kind of cool, and they just insert those features into the image, and that's what you get. So it's actually really, really trippy. Okay, so that's the result that you get. It's actually pretty cool. Okay, I'll let you stare at that for a little bit. Okay, the next application, I don't know if you're Android or iOS users, but there's an app which is called SwiftKey. I don't know if you are familiar with the SwiftKey app. Basically, how it works is you might notice how really good it is at predicting text. Like you type in a couple of words and then it predicts full sentences for you. And how it works is that it crawls your texts and it crawls your emails or anything that you use to write. And what it does is that it uses neural networks to train predictive models where it basically learns the way you speak so that when you type in a couple of sentences, it'll predict what kind of sentences you're going to say next. So for example, if you say, I am going, it'll say, if you text a line and say, I'm going to the store, or if I'm going to the gym, it'll infer that and say, do you mean this sentence or this sentence or this sentence? So it's actually a really cool application where it actually minimizes the amount that you type. So you just type in a couple of sentences and then it has a predictive model which will tell you, it'll predict what kind of sentence you're going to actually type out next. So it actually uses a neural network model to guess what you're going to say. So it's actually really, really a really cool application of neural networks. So Android SwiftKey. The actual predictive models that actually they talk about, it's in a white paper online, but it's actually, I figure that's a really cool application for neural networks. So it's the Android SwiftKey app. So the basic premise how it does is that it combs through anything that you use to, anything that contains text, whether it's emails or text that you send, or even crawls your Facebook account or your Twitter account, anything that requires you typing. So the app combs through email, social media, your accounts, not particularly anybody else, but texts, etc., and builds a predictive model for typing out sentences. So then all you have to do is just type out, a couple of words, and then it'll suggest completed sentences for you to type in. It actually saves a lot of time. So you type in a few words, and the app figures out the best guess to complete the sentence. And then what you can do is you can certainly override and say, well, I didn't mean to type in any of these sentences. I mean to type in this, and then it'll retrain itself and it'll relearn so that it adapts to particular situations. And also, it even depends on which app you're using. Like, for example, if you're opening up email, then there's this particular cache of sentences that it'll predict, or if you're typing in text, there's a particular cache of sentences that it'll predict to. So it's really, really adaptive, and it's a really fun app. So best guess to complete your thought. Okay, and then the last but not least, autonomous driving, the initial attempt anyway. This is actually one of the funnest applications of neural networks back in the day, the initial attempt. It was basically made by a guy from Carnegie Mellon University. It's probably one of the top universities in the United States for robotics and machine learning. It was created by a guy named Dean Pomerleau. So basically what they did was they took this army truck and they had a high-speed camera that was mounted probably towards the bumper or so, and it was taking high-speed pictures, like I think it was 30 frames a second or so, and it took a picture of the road and it also took into account the orientation of the steering wheel. So the training phase was you drive the truck around, it takes images and it figures out how you're orienting the steering wheel, and it correlates that with the current picture on the road. So that's how it's training. And then what it does is that during the testing phase, it takes images of the road and then it figures out how to steer the wheel based on the current picture of the road. So it used a neural network to train to figure out what pictures corresponded to what direction of the driving wheel that you're steering, and then it uses a neural network to predict or to steer the car based on what picture of the road you're looking at. So that was the initial attempt for autonomous driving. And if I have time, I'll show you a nice little video. It's actually really cool. From Carnegie Mellon University. So basically what you do, there was a high-speed camera that was mounted, and then it takes pictures every so often, and then it records the orientation of the steering wheel based on the picture of the road. So a high-speed camera took pictures of the road. And the orientation of the steering wheel. Okay, and then basically what you do is car would, oopsie, that's in, drive in the right direction. Based on the road picture. It was the initial attempt, but then there was, when you're driving, there are complicated situations such as what if there's like a fork in the road, or there's like a three-way cross, like how exactly do you handle that, right? So it only could handle simple situations where there's unambiguous left and right turns or going straight, but then when you're dealing with complicated situations, it kind of failed there. But at least it was an initial attempt, and actually it was pretty successful for very simple situations, based on the right road picture. Okay. All right, so I talked about all the cool applications. I actually haven't asked this question yet. So the question I've been meaning to ask is this: why do we need neural networks? So I talked about the cool applications, like how they're being used in the industry, or cool applications and all that, but why do we actually need them? What's the point? Well, I'm going to bring you back to about the early 70s. It's a classic problem which is called the XOR problem. So if you remember from 328 or the digital systems class that you talked about, you probably remember something which is called the XOR gate, the XOR logic gate. Basically what it means is that it's an exclusive OR where the output is true only if one of them is true, but not both of them. So if both of them are false or both of them are true, the output is false. But if either one of them is true, then the output is true, right? So record the XOR logic. So it looks like this. So you've got two inputs, X1 and X2, and then it kind of looked like that, right? This is the XOR logic gate. Sorry? Oh yeah, it was, I think it was like that, right? Yeah, there we go, that's it, yes. Okay, so Y is true, just making sure you're paying attention. If either X1 or X2 are true, but not both. Okay, so that's basically the whole premise of an exclusive OR. So let's write out a truth table, right? So you've got two features or two inputs, and then you have an expected output. So it's 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0, right? So you can think of this as like a binary classification problem, right? So you can think of 0 as being class 1, right? I'll give this with X's, and you can think of this as being class 2, having circles. Okay, so if I were to plot them onto, just a 2D plane, here's X1 and this is X2, all right? And then if I were to, plot these points, so I've got class 1 and class 2 here. Sorry, I wanted to do this in blue. So class 1 and class 2 are here, right? This is 0 and 1. And then I have class 2, okay? So far we've talked about decision boundaries, the best line to be able to separate between these two classes, all right? So what you've learned so far, there is actually no way you can take any line possible to be able to separate these two from each other, right? Because the decision boundary is a way to separate between two classes, right? There's no way you can give me any line that'll be able to successfully separate between these two without doing a misclassification, right? So with what we've learned so far, there is no way any decision boundary can separate the two classes, right? Like if I tried something like, this for example, let me try something like that. Well, that's not going to work because the red circle that's supposed to belong to one side of the line. The X's are totally fine, but then the circle is misclassified. That's not what you want. Or maybe I'll try something like this. Well, that's not going to work either because, well, you already have two misclassifications. Like this line can't separate between the two. Or maybe, I'll try something like this. That's not going to work either. So none of these will work. There's no way that you can have a decision boundary that'll separate between these two classes successfully without making an error. So this is what's known as the XOR problem. So what we've learned so far is just we wanted to try to find a line that'll separate between the two classes, but what we've learned so far, that's not going to work. All right, so that's why the need for neural networks came, because we have to go a little further. Instead of trying to find a decision boundary, you want to try to find a decision region where elements that are in one region are classified as one class and elements in another region are classified as another class. Okay, so that's the whole reason why neural networks came about. All right, so neural networks are a great way to realize nonlinear and complex, complex decision regions. So we're not looking for decision boundaries anymore. We're going to look for decision regions. So if we can realize these, then our problem is solved, right? So something like this could work. So something like this could work. Okay, so let me just take this figure and just copy it. Sorry. Something like this could work. So what you can do instead is maybe have, one region like this and like this. So then anything defined here, right? So here is, decision region for, y is equal to 0. And then you can have something like, this inside here, like like this here. And this would be the decision region for y is equal to 1. So something like this instead. So instead of taking a look at decision boundaries, we're going to take a look at decision regions, where points that belong to one region or one class, and points that belong to another region or another class. So we're going to think a little broader here. We can't take a look at boundaries anymore. We got to take a look at regions. Okay? So that simple model itself was the inspiration behind neural networks and the whole, that whole movement. So neural networks are what are known as biologically inspired models. They're inspired by the way the human brain acts, or the way the human brain, the certain actions that the human brain, takes on. Okay? So basically what we mean by biologically inspired models is that they are machines that act in the way the human brain does, right? So machines that act the way the human brain does. All right? Okay, so I don't know how much biology you know, but you know that inside our human brain, it's jam-packed with a very simple computational unit, which is called a neuron. So basically, neural networks simulate the way neurons behave, the way the human brain acts on them. Right? So they try to simulate how neurons act in the human brain. So they simulate the behavior of neurons So neurons are the basic computational unit inside your brain, and neural networks, they attempt to try to mimic this behavior as a computational unit. Okay, so let me just get a little diagram here. Okay, this I took from Andrew Ng's course. Okay, so basically our human brain is jam-packed with these neurons. Actually, the count, if I recall from ASAP Science, it said there was about 86 billion neurons that are jam-packed into your brain, which is actually pretty cool. So the human brain is jam-packed with these neurons. Okay, so the purpose of a neuron is to transmit signals from that particular neuron to other neurons in the human brain. So they're basically used as a way of propagating electrical signals throughout the human brain and also throughout your entire body, so that we're able to perform certain actions. So the human brain is jam-packed with these neurons. So the purpose is to transmit. Yeah, I'm not going to test you on biology and stuff. I just wanted to show you where neural networks come from, so you can take this as kind of like a bonus in terms of the theory in the course. Transmit signals to other neurons so we can perform actions. Okay? So basically neurons have they consist of many basic elements. So they have a cell body, right? And that cell body is basically this little guy right over here. This is the cell body of a neuron, okay? So basically you can think of a neuron as receiving signals, doing some basic processing on them, and outputting the signals to other neurons to be able to do actions. To be able to perform certain actions. So neurons have a cell body, all right? And basically we have these input wires which are called dendrites. So what these dendrites do, the purpose is to receive input signals from other neurons. So dendrites are, you can think of them in terms of engineering as input wires. They're input wires that receive inputs from other neurons. All right, and then you have these dendrites, which are input wires, and then you have the cell body that does the actual computation, and then the outputs are sent out through wires, which are called axons. So axons are the output wires that are used to send signals to other neurons that are in the human brain. Okay, so axons are, you can think of them as output wires. So there's input wires, there's output wires. So that send information to other neurons. Okay, so simplistically, the neuron is basically it's the basic computational unit of the human brain. It takes in electrical signals from other neurons, does some sort of computation on them, and then it outputs these signals to other neurons in the human brain. So you can do something meaningful. All right, so neurons are, computational units that receive inputs, work on these inputs, and produce outputs. Okay, so you have the axons here, then you have the, so this is the channel that the signals travel through, and then you have these axon terminals that basically connect to other neurons. So these connect to other neurons. This isn't a biology class, but I just wanted to give you enough information so you can understand basically what's kind of going on in the human brain. Okay, so neurons, can't spell. Neurons communicate with each other by sending electrical impulses. Or in biomedical engineering or in medical terms, they're known as sending spikes of information to other neurons. So by sending tiny electrical impulses. They're also known as spikes. Okay, so here's a little diagram. Here's a little blown up diagram of a network of neurons being connected together. So this is also pretty cool. Okay, so what's going on here? Let me just call this, I guess, neuron 1, and I guess we can call this neuron 2. All right? So basically how this works is neurons communicate with each other by sending tiny electrical impulses. So in this particular case, neuron 1 is sending a signal to neuron 2, right? So once neuron 1 does its computational requirements, it sends those signals to the axon to neuron 2. It does some sort of computational thing, and then it'll figure out which way to send the signals, whether or not it'll send the signals to your nervous system so you can move your arms or muscles, or it might send the signals to other neurons in the human brain so you can do other actions that are that might be related. Okay, so neuron 1 sends signals to neuron 2. Again, this is not a biology class. I just wanted to give you some idea of what's actually going on and how neural networks were inspired by these very simple computational models. Neuron 2 does some computation, and then decides where to forward the output. Right? So for example, these sets of axons might be connected to an arm, or these are dendrites, of course, they're outputs, right? These might go to a foot or something, like it just depends where. These might go to another neuron, for example. So they're all interconnected. Okay, so this is also, oopsie, how we control muscles. Okay? So signals, the outputs from the neurons are being sent to the nervous system of your spine, or the other neurons that are meant to receive signals for your arms, your feet. So that's pretty much how they work. Signals being sent to our arms or feet and so on, so we can move them. Okay, so that's all the biology that I'm going to talk about in this course ever. Okay, so that's how we can represent it in terms. That's how we can take a look at the human brain at a very high level. So let's get back to the actual course. So how do we represent a neuron in intelligence systems or machine learning or whatever you think of it? Okay, so these actually have a synonym. So when you talk about neural networks and machine learning, they're actually known as artificial neural networks, but they're actually trying to simulate the way human neural networks work. So we think of neural networks as being synonymous to artificial neural networks because that's actually what is being interpreted. But every time you talk about neural networks and machine learning, what they actually talk about are artificial neural networks. So you're artificially simulating the way neurons behave in the human brain. Okay, so artificial neural networks and neural networks are synonymous. So you can use one interchangeably without risking looking like an idiot. So these are what's known as artificial neural networks. Okay, because you're simulating the way the human brain works. You're not actually taking a look at the human brain itself. So these are almost similar to the human brain. Okay, so here's a quick example. So this is how we would represent it as a computational unit in machine learning. So we've got a bunch of input nodes or input signals. Let's just start with something very basic. We've got a bunch of weights, and I'll talk about these as I draw them out. And this is the output. Okay, So we call these the input units. Okay? And then there's a very special unit which is called the bias unit. You can think of that in terms of logistic regression or linear regression, where you have the slope, or the slope term, or the, not the slope, the intercept term that allows you to adjust where the actual decision boundary is. And this is usually equal to 1. So in neural networks, you have what's known as a bias unit. You have the input units. And then you could think of these guys here. They're basically input wires. Or you could think of them as the dendrites, so to speak. Right? And then you also have input weights. So each of these inputs are weighted by a certain amount that correspond to, the connection that is used between each unit and this guy. You can think of this person as the cell body. This is where the actual computation is being handled. And then you can think of this as the output wire. So this is very analogous to what you see in terms of a neuron in the human brain. So you've got some input units, you've got some input wires. They all get collected into the cell body, they do some sort of computation, and then the output gets forwarded to other neurons in the network. Okay, so there are 3 inputs. This is a very simple model. Obviously you can go forward and you can have as many inputs as you want and as many outputs as you want. So this is just a very basic model, but we can certainly generalize. So there's 1 output, okay? And you can think of G as the cell body. Okay, that does all the computation. With the inputs. In machine learning and in neural networks, this is a very special name, this cell body thing. It's what's known as the activation function. So the activation function will take in these inputs, do some sort of computation on them, and output them to other parts of the neural network. So this thing has a very special name, and it's called the activation function. So also called the activation function. Okay? So G is what's known as the activation function. Okay, so basically how this works is you basically take each of these inputs and then you weight them by certain amounts. So x0 gets weighted by w0 and x1 gets weighted by w1 and so on. So you take all these inputs, you weight them individually, and then you add them all together. Add them all together, you put them through the activation function, it does some sort of computation on this sum, and then it outputs a final value that you use to forward to other neurons in the network. Okay, so the inputs are weighted by the weights, the corresponding weights, summed and sent to the activation function. So basically the output looks like this. So the output Y is you're going to basically take each of these inputs, you're going to weight them individually. Okay, you're going to add them up, and then you're going to apply the activation function to it. So once you add everything up, you submit it to the activation function, and then it outputs some number. Okay, these weights here, so these are weights. You can think of them as the parameters. So when you took a look at linear and logistic regression, the point was to find the right set of parameters that will be used to separate, one class with another. So these weights are also called parameters. So it's very synonymous. So when you take a look at certain textbooks, when they talk about trying to find the right weights or trying to find the right parameters, they mean one and the same thing, right? So these weights are also called parameters. And then the input units, right here, these guys. So these input units, they're also called nodes, which kind of makes sense if you take a look at the picture. So when I use input units or when I use nodes, I'm going to use them interchangeably. They pretty much mean the same thing. Okay? Now, and then this here is the activation function. There are many possible activation functions you can use. It just depends on the application as well as the type of data that you have. So there are many possible activation functions, and they all have to satisfy a certain property. They have to be, continuous and differentiable, and they have to be also within a certain range, but that's okay. Possible activation functions. Okay. The two most common ones are the sigmoid, which you are very familiar with. You use this in the logistic regression model, right? So this is just 1 over 1 plus e to the minus z. You're very familiar with that. There's also something which is called the hyperbolic tangent. You might have talked about hyperbolic functions, back in first year, and you probably haven't used them again after that. But they do serve a purpose, and this is one of them, hyperbolic tangent, or tan h. So this is equal to e to the z minus e to the minus z over e to the z plus. Okay, so you have the sigmoid, you also have the hyperbolic tangent. Okay, and I'll talk about what these are in a minute, like in terms of behavior, but I just wanted to lay these out. So, and there's also something which is called the perceptron. So this is also a biologically inspired model, so it's based on how neurons fire in the brain. So it's a very simple model. It's basically like a step function in 532, where the output is 1 if the input is positive, and the output is 0 if the input is negative. So it's very simple model, the perceptron. So let me just show you what these look like. All right. So you have the sigmoid function, which is here. You're very familiar with this one, right? And then I'll give you what the tan h function looks like, or the hyperbolic tangent. Okay. And then we also have the perceptron, which kind of looks like this. So let me just 0. It looks like that. Very simple. This is Z. This is perceptron. Okay, so if you take a look, the shape between the sigmoid and the hyperbolic tangent, they're pretty much the same. It's just the dynamic range between them is different. So the sigmoid, the range of the vertical axis was between 0 and 1. But the hyperbolic tangent is basically a scaled version of the sigmoid. And you can see here that the range is actually between -1 and 1 instead. But the shape is pretty much the same. It just depends on what problem you're considering and what data you're using. But you can use either the sigmoid or the tan, or you can use the perceptron into which. It just depends on which, what kind of data you're looking at. So you can think of this as tan h is like the sigmoid, but the range is between -1 and 1 instead of 0 and 1. Okay, so this is the graphs of G, I guess. Okay, so here's something interesting that you may or may not have noticed. If you take a look at this very simple model, right, you can think of a single neuron as logistic regression. So if I made the cell body or the activation function the sigmoid function, and if I made this bias unit and this weight equal to 1, then if you actually did this computation, you can think of that as actually being logistic regression, of just using a single neuron where the bias and the weight is just 1, and the activation function is a sigmoid. So if you actually use that particular situation, then you can think of a single neuron as being logistic regression, which is actually quite nice. All right? So note. Logistic regression is exactly, okay, this is, keep sniffling, it's a little annoying. At least for the video anyway. Okay. Logistic regression is exactly the same as using a single neuron. I'll take a break soon, a few minutes. If the bias unit and the weight are equal to 1, and we have n inputs, n plus 1 weights, and 1 output. Also, the activation function is the sigmoid. So you can think of that. You can just think of a single neuron with the sigmoid, as well as making the bias unit 1 and the weight 1 being logistic regression, which is actually pretty cool. All right, that's just something to, something on the side, but you don't have to really know.
Sir,
Yeah.
why would we not have n inputs and n plus 1 weights in a single neuron? Because don't we have 1 weight for every input?
Oh, of course, yeah, for sure. Yeah, I'm just putting that there as a general, yeah, so you can, that's really extra, you can get rid of that if you wish, but yeah, there's supposed to be n inputs going in, but then you make the bias unit 1 and the weight 1, and then if you make the activation function sigmoid, then that is logistic regression. Yeah, but yeah, that's a little, yeah, that is extra, I just put it in just to be complete, but you are certainly correct. Okay. So, just one neuron doesn't work, usually not enough. Usually in very complex applications or very meaningful applications, you consider a network of neurons from, that are all interconnected together to be able to do something meaningful. And that's what we're interested in, okay? So a typical neural network has several neurons. Interconnected together. In different layers. So the layers is key. Okay? So what we're going to deal with in this course is only the situation where we deal with what's known as feed-forward networks. So the weights are interconnected together, but we're assuming that there are no loops. So there's no weights that connect to themselves, or they don't connect to any of the other layers in the previous layer or so. All the weights move forward. There's no loops, and they don't loop back to any other of the neurons in the network, because that actually is a little more complicated. And there are certain applications where you can loop back, but we're only going to deal with feed forward because it's the most simplest, and you can still do a lot of meaningful stuff with just feed forward. So in this course, we will only deal with what are known as feed forward, because all the information is moving forward. None of the information from the neurons are going back into previous neurons or looping with themselves. They're only going forward. Forward is the only direction. Okay, so feed forward neural networks. Okay, so basically what I mean is no connections with loops, no connections with loops. Okay, so this is what a typical one would look like. Very simple one. So the notation is a little different. I'm going to talk about it as we go. But this is pulled from Learning from Data, the textbook by Yasser Abu Mustafa, which is a really nice textbook. So Learning from Data by Yasser Abu Mustafa. Okay, this theta here are the actual activation functions. So let's just replace these all with G, okay? G's. Okay, and this would be the output. And then they're using the hyperbolic tangent here as the activation function. Okay, so basically you have a bunch, so this is how a typical configuration would be. So there are 3 types of layers. The first layer, which is known as the input layer, we're going to index it by 0. This is where your inputs come in. So if you have, let's say, a training example, and then each of these neurons are basically one feature of the training example, you take these inputs and you put them into the input layer. So these are where the inputs go. So inputs go here. Okay? And then you have a bunch of neurons that are interconnected, then each of these neurons, as they're connected together, they're separated by what are known as layers, okay? So any of these, so we have an input layer, and then we also have what's known as an output layer, and this is where you see the predicted result, or this is where the output of the computation is received that you can take a look at, and then you can do stuff with it, right? So output is observed here. In this case, we only have, one output neuron, and then these neurons here, they are connected in terms of layers. So these are known as hidden layers because we don't actually directly interact with them. But there are networks of neurons that are connected together in what's known as layers. So you have 0, which is the input layer, and then you have capital L, which is the output layer, and then you have a bunch of hidden layers of neurons that do computations for you. So in this particular case, L is equal to 3. Okay? So we have 4 layers of neurons. So we have an input layer, which is 0. We have an output layer, which is 3. And then this is indexed by 1 and 2. And then this is 0. Okay, so let me just write some notation here just to be sure. So notation. So notice that here, so the input layer, if you take a look, all of the neurons that are connected. So if you take a look, the bias units are not touched. So if you take a look in terms of the input layers, so you see the first feature, the second feature, and so on. None of them are being forwarded to the bias unit. The bias unit is left alone. It is used primarily just for getting the right decision regions correct. So there's no signals that are being forwarded to any of the bias units. The bias units are used to serve as inputs into other neurons, but they are never used to receive inputs. They're only used to send. Okay? So you have the input layers here. So notice that each one of these neurons are connected to every other neuron. So for example, we have 4 neurons here for the first hidden layer. And then if you see, we have the bias unit that sends a signal to each one of these neurons. Okay, except for the bias. And then each of these lines, you can consider them as a weight. Right, and then you can, you have another neuron here that does the same thing, right? And then so on and so forth. So each of these neurons are connected to every single other neuron except for the bias. So there are no missing links, right? So the layers are labeled. Okay, let me just write down some notation and then we'll take a break. So labeled by L is equal to 0, 1, 2, all the way up to L, okay? The first layer, which is layer 0, is what's known as the input layer. Okay? So this is where the inputs come from. Okay? And then the output layer is indexed by L, and this is the output layer. And this is where you actually see the predicted outputs. So there's many different architectures. There doesn't have to be just one neuron for the output. There could be 2, 3, or 4. It just depends. And we'll talk about how exactly you choose the architecture later, but I just want to lay out this notation before we proceed. So this contains the predicted values given the inputs. Okay, from the input layer. Okay, and then all the other layers, all the other neurons. So we've got let's see here. We've got between 1 and L minus 1. These are what are known as the hidden layers. The reason why they're hidden is because we don't actually directly deal with them. The hidden layer does the computation unit based just on the inputs of the input layer. The hidden layers are based, they communicate with each other, but we can't actually directly interact with them. So these are called hidden because we don't directly deal with them. Okay? All right. So with each layer, there's a certain number of nodes or a certain amount of neurons per layer. All right, so the nodes are labeled by 0, 1, 2, etc., etc. So the 0th node is the bias unit. Okay? And then it goes all the way up to, we're going to call this D sub L in the layer. Okay? So the term D sub L is the total number of nodes or the total number of neurons in layer L. Okay, so let me just write down that notation too. We'll just lay out all this notation, then we'll take a break. All right, so the value D sub L here tells you how many nodes or neurons there are in layer L. So we'll talk about the architectures later. How do you figure out how many hidden layers you want or how many neurons per layer? We'll talk about that later, but I just want to lay this out. Okay, so it tells you how many nodes or neurons are in layer L, but then it excludes the bias unit, so without the bias unit. So this is not counted. Okay, so therefore each layer has DL plus 1 nodes to account for the bias. Okay? Okay, so let me just pull up the example again just to be sure we're on the same track. So here, all right? So the number of nodes in the input layer, it's called D, all right? And the number of nodes in the first hidden layer are just 3. Okay, we don't count the bias. And then the second one is 2, and then the last one is just 1. Notice that there's no bias unit for the output layer as well. So let me just write that down too. So input layer has no inputs coming in. Okay, there's only outputs. So you usually initialize these to something, you know, the training example that you're looking at, and then it just sends this information through the network. So input layer is no inputs coming in, only outputs. And usually the bias unit has an output of 1. Okay, just a couple more notes. Let's see here. Actually, each arrow tells you the weight or strength between a node in one layer to the node in the next higher layer, to the node in the next higher layer, next highest layer, I guess. Right? So no bias unit for the output layer, or the output layer. And one more note and we'll take a break. And then finally this. The output of a node in a layer is fed directly to all other nodes. I just talked about this, to all other nodes in the next higher layer, except the bias. Except the bias. Okay, so this is important as well. So, okay, so if you take a look at the diagram, so each output that the neuron has, what it does is that forwards it to every other neuron in the next upper layer, except for the bias itself. So for example, if we take a look at this particular unit over here, you notice that it forwards its output to every single neuron in the next layer, except for the bias, right? So for example, this one here, it forwards the output into these two neurons here, except for the bias. So there's no bias unit for the output. The input units only have outputs. That's where you put the particular training example you're looking at. And then the output of each neuron gets fed to every single node or neuron in the next layer, except for the bias. Okay? Okay, we'll take a little break and then we'll dive into this a little more. Okay, let's take a 10-minute break and we'll come back.